Now in this video, we are going to learn about constraint equations. These equations establish relationship between various objects connected by strings. Let's start with a simple case. This case is very simple and this is just to learn the technique. This is one pulley. There is a mass M1 hanging here, another mass M2 hanging here. Simple Atwood machine, the first problem we learnt in Newton's laws. So now we want to establish the relationship between acceleration of M1 and M2. We know that the accelerations are equal in magnitude and opposite in direction. That is very obvious because if M2 comes down by 1 centimeter, M1 will go up by 1 centimeter in that same time because the length of the string remains constant. So how do you get the equation? The first step is to draw a fixed line at the topmost pulley. And remember, all distances must be measured from this fixed line. So everything we are going to measure from here. The distance to M1, we'll call it x1. So this is x1. And the distance to M2, we'll call it x2. As these masses move, the length of this string remains constant. So x1 plus x2, which will be approximately equal to the length of this string, L1, and that will be constant. So this is the string constraint. And if we differentiate this equation with respect to time, we'll get V1 plus V2 equal to 0. Remember, differentiation of a constant with respect to time or anything else will be 0. So V1 plus V2 is 0. From here we get the velocity relationship V2 equal to minus V1. As simple as that. Now if we differentiate this equation once more with respect to time, then we'll get A1 plus A2 is equal to 0. This implies A2 equal to minus A1. So this is done. We know the relationship between the two velocities. We know the relationship between the two accelerations. They're as simple as that. Just go step by step. In physics, everything is simple if you go step by step. Let's consider a slightly more difficult case. We have got one pulley here. A mass M1 is hanging here. Another pulley is hanging from this pulley. And here is M2 and here is M3. We want to get a relationship relating the acceleration of M1, M2 and M3. Again we follow same steps. Draw a fixed line at the topmost pulley. And everything we are going to measure from this fixed line, right? Not from anywhere else. The distance to M1, call it x1. Distance to M2, call it x2. And distance to M3, call it x3. All distances from fixed line. That is very important, not from anywhere else. Now we'll write the equation for each string. This string starts from here, goes down like this and ends here. So length of this string is this plus this, approximately. Now this is a pulley. This distance also, we have to give it a variable name, so we give it x4. Okay, after I complete with all the masses, then you can give the distance to pulleys variable names. So if you look at the length of this string, this first string, this is x1 plus x4. So we get x1 plus x4 equal to L1, right? That is the length of the first string. And this is a constant. If you differentiate this twice with respect to time, you'll get A1 plus A4 equal to 0. Therefore, A4 Therefore, A4 is equal to minus A1. So this relates A4 and A1. We can call this equation 1. Now we look at the length of this string. Left hand side, if you see, is x2 minus x4, and right hand side is x3 minus x4, right? So the length of that string is x2 minus x4. That is your left hand side, this one. And the right hand side is x3 minus x4. And this will be equal to L2. If you simplify this, you get x2 plus x3 minus 2x4 equal to L2, right? We differentiate this equation again twice with respect to time. So we get A2 plus A3 minus 2A4 equal to 0. But what is A4? A4 is minus A1. Therefore, we get 2A1 plus A2 plus A3 equal to 0. This is the relationship between acceleration of M1, M2 and M3 in this case. Very easy. Important thing to remember, always measure distances from the topmost pulley, and as the masses move, the length of each string remains constant. So we write those equations. If we differentiate once with respect to time, we get the velocity relationship. If we differentiate twice with respect to time, we get the acceleration relationship. This is how we apply constraint equations to solve problems. Now let us look at a slightly more involved problem. This is one pulley here. From this side, one more pulley is hanging. And from here, one more pulley. Don't get scared. It is simple. Here is mass M2. And these strings are all connected to mass M1. So this is the situation. It will look a little bit scary, but nothing to get scared. We apply the concept in a step-by-step manner, and that will be very simple. First, draw a fixed line at the topmost pulley. That is the first thing we learned. Any problem like this, draw a fixed line at the topmost pulley. Then call the distance to M1 as x1. So this is x1. Remember, all distances from the fixed pulley. Then the distance to M2, we call it x2. You follow this logic all the time. Now there are two extra pulleys. So we can call this x3. And the distance to this pulley as x4. Now look at the strings one by one. This is one string. As these masses move, the string length will remain constant. This side you have got x1. That side you have got x3. So x1 plus x3, which is the length of string 1, that will remain constant as these masses move. And you differentiate this equation twice with respect to time, you will get A1 plus A3 equal to 0. This implies A3 is minus A1. See, A3 is an intermediate variable, so you want to eliminate that. That's why we are writing an equation for finding A3. Now look at the second string, this string. This left hand side is x1 minus x3, and this right hand side is x4 minus x3. So for this the equation is x1 minus x3 plus x4 minus x3 is equal to L2, length of that string. To simplify this, you will get x1 plus x4 minus 2x3 equal to L2. Again we will differentiate this equation twice with respect to time. So we will get A1 plus A4 minus 2A3 equal to 0. But what is A3? A3 is minus A1. So we can put in this equation A1 plus A4 minus 2 minus a1 equal to 0. So 2a1 plus a1 will give us 3a1. So a4 becomes minus 3a1. Why we found a4? Because a4 is an intermediate variable. You must understand why we are doing a particular step. So we found out a4 because a4 is something which we don't want in the final answer. Now look at the third string. This is the left hand side. x1 minus x4. Right hand side. x2 minus x4. Therefore, x1 minus x4 plus x2 minus x4 will be equal to L3. Length of the third string. This is string 1, string 2, string 3. Only 3 important strings. This is there but not important for us. So now what do we get? We get x1 plus x2 minus 2x4 equal to L3. We can differentiate this equation again twice with respect to time. a1 plus a2 minus 2a4 equal to 0. a4 we know, minus 3a1. So a1 plus a2 minus 2 minus 3a1 equal to 0. So what do you get? Here you get 6a1 plus 1a1 here. So a2 becomes minus 7a1. So we have found the relationship between acceleration of 2 and acceleration of 1. Acceleration of m1 and acceleration of m2. Now, can we get this more easily? So let us try to write the tensions. If the tension here is T, what will be the tension here? Same string, same tension. So T again. This will be T. This will be T. So what will be this? This will be 2T. Right? Pulleys are massless. So the tensions have to be balanced. So this is 2T. Now this is 2T. This is 2T. Same string, same tension. Tension here has to be 40. Here 40. Here 40. Here it is 80, but I am not that interested in this one. So this will become 40 again. This is 2T because this string is having tension 2T throughout. One string, one tension. Massless string, massless pulleys. Okay, that is our basic assumption. So what is the total tension on this M1? 40 plus 2T plus 1T. So 40 plus 2T plus T. How much is that? 70. Total tension on M1 is 70. What is the total tension on M2? That is T. Wherever the tension is 70, put the acceleration as A. Where the tension is T, the acceleration will be 7 times A. This trick you just remember. Where the tension is 70, put the acceleration as A. Then where the tension is T, the acceleration will be 7A. This will work for these kind of problems. Earlier we have learned that if somewhere the tension is 2T and the acceleration is A, then in that same system, pulley system, where the tension is T, the acceleration will be 2A. So this way we can get the acceleration relationship very quickly. But this is the proper method to get the relationship between acceleration of M1 and acceleration of M2. So we have learned how we can get the relationship between accelerations of various objects connected by strings. Same concept is valid for finding the relationship between velocities of various objects connected by strings. This is called constraint equations.